Okay, let's move on to the next speaker because we're already behind schedule. So last but not least, thanks, Nahum. So the final speaker would be Mikolaj Bojanczyk from University of Warsaw in Poland.
Thank you. Thank you very much. Let me try to share my screen. Is it working? Can you see my screen?
Yes.
So thank you very much for the honor of speaking at this event. I am, like many people working in my field, very much indebted to the work of Boris Trachtenbrot, and so it is a great honor for me to speak here and talk about a bit of history and a bit of my own personal work later on. So the title of my talk is based on a quote, well, a very short quote from Trachtenbrot, which is about an approach to, well, automata. So let me begin with another quote, which you can find in the famous Rabin and Scott paper about non-deterministic automata, where they start out by saying that there has been a lot of recent work on automata. And however, we have adopted, but the trouble is that they have some outputs, these automata. But they simplify it. So we have adopted an even simpler form of the definition by doing away with a complicated output function and having our machines simply give yes or no answers. And well, this has been very much adopted. And now when people speak of automata, they use them as yes-no devices. But originally it was not so, I think. In many of the old papers, they frequently just output some values which are not necessarily yes or no, and therefore they can be seen as sort of transducers, so where they transform an input string into an output string, maybe. And you can see that Trachtenbrot sort of disagrees with this. So you can find this quote in his autobiographical note from, I guess, a previous instance of these celebratory workshops, where he writes that counterbalancing this algebra of languages philosophy, I followed the logic of operators view on the subject, suggested by Burks and Wright, where they focused on the input and output behavior of logical nets. And it is indeed, for example, in a famous Trachtenbrot paper, where he's one of the people to prove that monadic second-order logic is equivalent to automata in the late 1950s, you can see this approach. And so that's the reason why I talk about the logic of operators here, because I think that this view of automata as not just saying yes or no, but being transformations is very fruitful, and even today it is. So I will begin with a more technical discussion about the most basic way of thinking about automata as not just acceptors, but also as functions, which is the one that was used, refers to by in the quotes that I mentioned previously, which I think is currently called Mealy machines. So a Mealy machine is the simplest kind of transducer you could imagine. It's like a deterministic automaton, but it doesn't, instead of accepting states, it has, every transition has an output letter. So it's sort of like if there would be two output letters, yes, no, then you could think of that as a subset of the transitions. But a Mealy machine says, well, maybe there's more than two values. Maybe there's like, well, and these possible values are output letters. So this automaton, when it inputs a string, at any given moment, it just produces, for every input letter, it produces one output letter. So it's a string-to-string function, which is then preserved. So that's the most basic model of transducers you could imagine. And this is already a very nice model. And I think some important results about it are not part of the completely basic automata curriculum, as I think maybe they should be. So here's, I mean, everybody's heard of this result, but it's actually, and it's not the one that I will talk about in a moment, but I think it doesn't get the attention, research attention that it could maybe even nowadays, which is about decomposing. So, and composing them. So Mealy machines, they're transducers, and what you can do with transducers, you can compose them. So if you have a Mealy machine, that inputs words over some alphabet and produces words of another alphabet, and then you have a second one, then you can compose them and get a third mini machine. This is a very easy construction to do. It's a product construction which does this. And this kind of, the fact that you can just literally compose them is very useful to express something. So here's an example that maybe not everybody is familiar with. It is the following. Suppose that we have a finite set of mini machines, and they happen to have the same input and output alphabet. They also happen to have the property that they define bijections. So there are permutation of strings. So every output string is possible, and so it's injective and surjective. So there's a one-to-one correspondence between input strings and output strings. And therefore, if you start to compose these devices, then they give you a group, a subgroup of the permutations of all possible strings. And in fact, in group theory, this has been quite a nice approach. And for example, there's a famous example in group theory of Grigorczyk's group, which is a solution to the Burnside problem, which is of this kind. So you can define nice groups by composing transducers. So that's one example, a bit maybe not central to automata theory, but nice to know. But something that is definitely central to automata theory is the fact that you can decompose mini machines. So it's the same picture, but in the opposite direction. Suppose I have a mini machine C, then I could potentially decompose it as a composition of two mini machines. And this view is underlying the famous Chronology Theorem, which tells you that every mini machine can be decomposed, well, maybe not necessarily into, but finitely many mini machines, such that each one is either reversible, which means that if you look at the state behavior, then you can always go back in time. So if every input letter gives you a permutation of the states and some output, so those are reversible mini machines. Or you have some others which have two states and they have other properties, but let's just keep it simple for the moment. They have two states, and they're roughly speaking the until modality of LTO. So this is a rather famous theorem. I think many people have heard about it, but it is actually surprisingly easy to show, contrary to its reputation. And I think it is super fruitful, and I think it should be part of even modern research toolbox in a way that I will try to argue in the next slides. So that's about a bit like this is very old stuff, more than 50 years old. But it can be quite relevant now in trying to compose and decompose machines, as you will see in a moment, with some maybe more recent applications. So here is a more recent class of transducers. It's also not super new, but it's well, new enough, I would say. Let's pick it appeared well in steps. I mean, I guess that the original model is like even very, very old, but the main interest has been, at least in this century, which is consider the following models for defining string-to-string functions. Well, you start with one that is super old, that dates back to the 50s, which is actually in particular Rabin Scott's paper, deterministic two-way automata with output. So I know you have a head and you move around, and you once in a while you can produce an output letter. So for example, you can reverse the string by going to the end and outputting in the opposite order, or you can duplicate it by outputting it once, returning and outputting it again, and do all sorts of things like that. So that's a very, very old model, which has been studied since the 50s and 60s. But then Engelfried and Hohebaum, they observed that this is the same thing as a seemingly completely different thing, Mso Transactions, which is a formalism that originally appeared mainly for graphs in Courcelles' work, but you can also use Mso Transactions to transform words into words. If you're not familiar with Mso Transactions, well, the idea is that it's like usually one uses MSO to say yes or no to an input word, but you can also use it to define a new word. And the idea is that some positions of the input word will be used as positions of the output word. So you have an MSO formula which tells you which positions of the input word will be used as positions of the output word. And then you have to define a new order because maybe you want to order it differently. For example, you want to reverse the input word. And then you so you give that by an MSO formula which tells you which position, the order on positions of the input word, which is the new order for the output word. And then you have maybe you assign new labels. So basically you describe the structure of the output word by using logic. And they prove that it's the same thing. And then along came Allure and Czerny, and they gave a very nice operational model that goes, is a one-way model called streaming string transducers. So it's a DFA which keeps several registers which store pieces of the output string and rearranges them and concatenates them. And they showed that this is equivalent to R3. We have a very nice class of string-to-string transformation. It's a nice theory, non-trivial, and that has been subject to, well, somehow it's very old, but it's been subject to a lot of recent attention. So this is, I think it's called regular functions. This name was proposed by Engelfried and Hellebom to say that this is a central model of transducers. And it's been quite subject to quite a lot of recent attention. So one very nice thing about regular functions is that they're closed under composition. It's not obvious to see. I mean, this was a question which was already posed for deterministic two-way automata with output since they were around for quite a long time, and it was proved, I think, in the 70s that they are closed under composition. But this is it's non-trivial combinatorially. For Mso transductions, I guess it's kind of clear because the model is designed to be closed under composition. But again, if you would like to prove it directly for streaming string transducers, this is again a non-trivial result. But since they're all equivalent, they're all closed under composition. And since they're closed under composition, well, it's also meaningful, especially meaningful to ask how you can decompose them. And here's a straightforward, well, okay, maybe not straightforward. Here's a version of the Chronology Theorem for regular functions, which is that you can, like in the Chronology Theorem, you can decompose them into basic devices. So one of the basic devices is media machines, which themselves can be further decomposed. Thanks to the Chronology Theorem. And well, another device that you might want to have is monoid homomorphisms. Very simple thing. The idea is that media machines are letter to letter, and regular functions not necessarily. So monoid homomorphisms are something that allows you, for example, to increase the length of the input by a factor of 2, make it 2 times longer, because you can map each input letters A to say to output AA or whatever you want. Then you need 2 more operations, which are the following. It's map reverse. So imagine that you think of your input string as a list of strings, and then you reverse each one of them. And there's like a separator symbol which tells you when you need to go from reversing one string to another one. And map duplicate is the same thing, except instead of reversing each string on the list, you duplicate. Okay. And then it turns out that this is exactly what you can do with these models. So it's like a Chronology Theorem, which tells you that these are the prime functions. And that, as you remember, the Chronology Theorem tells you that media machines, you can replace them by reversible media machines. So if for some results, for example, it is easy to prove them by induction on, just decompose something into these atomic devices and prove the result only for that. That's some way of using it, but I think more importantly, it explains sort of what you can do. So that's regular functions and well, the logic of operators. So how you can, I mean, logic. What's logic? Logic is you have some properties you can express, and you have some combinators which tell you how you can modify already expressed properties into new, bigger, more complicated properties. And transducers are sort of the same. So it's interesting to identify the prime transducers, and this is what I just discussed for regular. Okay, and the last thing I wanted to say is a third class of transducers, which is maybe the most recent one, which is motivated by the following remark. If you look at regular functions, the ones that I just discussed, they have linear growth. I mean, there's several different models, and in each one of them, it's rather easy to see. For example, if you take the definition by deterministic two-way automata, I mean, if you are a deterministic automaton, then you cannot visit the same input position twice in the same state, because otherwise you would enter into an infinite loop and you would not produce any output. Every deterministic automaton has, well, the output size is at most 2 times larger than the length size of the state space, which is fixed. The other models are also designed to have linear growth. And it would be nice to have a model which is kind of similar, so also had a good, robust theory and many different characterizations, but which would go beyond linear growth and have polynomial growth. And this can be done, and this is a class of functions that I would call polyregular functions, and I will explain to you in a moment. So the idea is that it's supposed to be the regular functions, not for polynomial growth. So here's the definition of the class, which can be expressed by the following theorem, which gives you several equivalent models. And since they're equivalent, they all describe the same class, and this class can be called polyregular. So let me begin with the first one, which is 4 transducers. So what's a 4 transducer? Well, consider the following program. It's like it's an imperative programming language which has 2 types of variables. You have variables which range over positions, and Boolean variables which positions of the input string, and Boolean variables which store true or false. And this is basically just writing a for program for a mealy machine, roughly speaking, which just goes through all positions of the input string from first to last. And then in the variable p, it stores the parity of the input position, and so it gets negated in each moment. And then whenever the parity is even, or I think odd, then it outputs the input position. So what you can do here is you can loop over a position in the input string, and then you can ask what is the label of that position, and maybe depending on your state, which is the Boolean variables, you can do something. So that's a very simple for program. Here's a more complicated one. It outputs all suffixes of the input string in growing order. So it begins, I think, with the longest suffix, which consists of the all string, and then it gets shorter and shorter, and at the end it gives you just a very short suffix, it's just one letter. So how does it work? Well, you also have for loops, but you're allowed to have several for loops. You can nest them, and as you would in a programming language. The external loop ranges over all positions in first to last order, and then the inner loop ranges over all positions in last to first. And then if the inner loop is later than the outer loop, then you output the position. And I hope that this gives you a suffixes. So this is just an example, but generally speaking, 4 programs are this. So you're allowed to have loops, which loop over positions of the input string in first to last or last to first order. You're not allowed to write to these position variables in any other way. You can just, they're just read-only. The only way to write them is to loop over them. And you can compare them, ask what is the position of the input string at a variable, and then you can output stuff, and you have Boolean variables. So that's a for program. It defines a class. There's some functions you can do that with. That's one definition of the class. Another definition is a model that has been around, I think, since the 80s or 90s, starting out with the work of Gloverman and Harel, which is deterministic pebble transducers. So the idea is like you have a multi-head automaton. However, the heads have a stack discipline. So there's like a head 1, head 2, head 3, and you're not allowed to move a less important head. You're not allowed to move a more important. They're like the heads are on a stack. So you can push a new head to the stack, and you're only allowed to move the head that is at the top of the stack. Okay? And when you're moving it, you can ask how does it relate to the positions of the heads which are deeper on the stack, but you cannot move any head that's deeper on the stack. And the stack has constant height. That's very important. So that's like a generalization of two-way automata with like a stack of heads of constant height k, and then you can think of that as a transducer. And it clearly generalizes for transducers because the state of a deterministic pebble transducer can be used to store the Boolean variables, and the stack is what are the positions of the variables in the loops. However, it seems to be strictly stronger because in a deterministic pebble transducer, your pebbles can move forward and backward, while in a forced transducer, they're just constrained by the syntax. They can only move to the right or to the left. They're sweeping. However, it turns out that the two models are equivalent. Of course, well, maybe not, of course, but it's true. You will need to have more nested loops than you have pebbles if you want to go from deterministic pebble transducers to forced transducers. Then there's another model, which I don't have time to describe, which is a kind of Mule Calculus. So imagine you have simply typed Mule Calculus, but you have a string data type constructor, and then you equip it with some string manipulating operations such as concat, which takes a string of strings and gives you a string. And then it turns out that this is equivalent. It's a higher order Lambda Calculus. It's equivalent for transducers. And there's another model, which I think is maybe a bit surprising, which is Mso Interpretations. So what's an Mso interpretation? It's like an Mso transaction, but you're allowed to, in an Mso transaction, every position of the output string is interpreted in one position of the input string, hence linear size output. Well, why not interpret one output position and say a triple of input positions, and then you have cubic size output. So here I will give it here's a definition. So we use a classical approach of MSO where you model a word as a structure. So the universe of that logical structure is the positions of the word. They're ordered a linear order and unary predicates for every label. Battery size. And then so this is the classical approach used in thinking of MSO. And an MSO interpretation, here I'm thinking of string-to-string MSO interpretation, so you have an input alphabet sigma and output alphabet gamma, and it's given by a dimension. So in MSO transduction, this dimension is k equals 1, but here we allow k to be bigger. And the idea is that every output position is going to be described by a k tuple of input position. And then for every output letter, you have an MSO formula which inputs k position and tells you, does this k tuple should have label A? And then you have an order formula. So it takes two k tuples of input positions and tells you, is k tuple x is before k tuple y? Okay. So this, I mean, if it's well formatted, and you wanted to create strings in the sense that for every input string, the structures that is described by these formulas happens to be a string. So then it gives you a string-to-string function. So you might ask, I mean, it's a very natural model. For example, first-order interpretations. This is like first-order interpretations, but to MSO. So you might ask, why hasn't this thing been? The reason is that if you have experience with MSO, you would never propose this definition. It doesn't seem to make sense. For example, it shouldn't be closed under composition, but in fact it is closed under composition. Why should it not be closed under composition? Well, imagine you want to compose two such interpretations. Then if you think about the second one, and if the second one is quantifying over a set because it's using MSO, it seems to be quantifying over a set of tuples because positions of the intermediate word are tuples of positions in input word. And that shouldn't be okay. But it turns out that it does work because, as the theorem says, MSO interpretations are equivalent to all of the other models. In particular, all of this thing is closed under compositions. So it should say here that polyregular functions are closed under composition, which is, I think, rather remarkable that MSO interpretations are closed under composition. And you can also have a Chronology theorem for them. So every polyregular function can be obtained by composing the following kinds of functions. So regular functions, and which themselves decompose simpler functions. And then one more function, which I would call squaring, which is you input a word, and then you, well, for every position in that word, you output it again with that position underlined, as here. And if you just compose regular functions and squaring, maybe it's like one squaring, then one regular, then one squaring. And in fact, you can just start off by square, 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 and then one regular function. That would be enough. And that's a Chronology theorem here. So that's this is like a relatively recent class of string-to-string functions. But again, it seems to be very fruitful to start thinking about not just regular languages, but about transformations and words and seeing how they can. Okay, I think I will end here. So I guess if you have any questions or comments, I'd be happy to have those. Thank you.
Thank you very much. Any questions? How do you, just random, how did you come up with this correspondence? Where did you start from? Which one?
So, okay. I was aware of, so Pebble transducers are an older model. And I think I was aware of those, but I forgot about them. But I was thinking about Mso interpretations, and I was thinking, well, the first instinct is this cannot work. But then if you look at examples, it seems to start working. And then you start working on it. You work more and more, and then you realize that it turns out to be a very robust and well-behaved class of functions. And then you, okay, now, okay. I started talking before thinking. So let me come back. Now I remember exactly how it came across. So it started with the Lambda Calculus. How? Well, Lambda Calculus, or maybe Chronology. It is very close in this particular context. So I previously had a Lambda Calculus which described regular functions, the linear ones. I didn't talk about it, but I had a Lambda Calculus characterization. And then the thing is that once you work with expressive models such as Lambda Calculus or anything that closes under composition, the typical setup is if you add one thing, then it either blows up completely and becomes Turing complete, or it doesn't change at all. But then squaring seemed to be a strange thing. You add it, it does change, but doesn't blow up completely. So, and if you have a very robust system, then you expect the class to be nice, and there were no surprises here. So sorry for
okay, thank you.
A rambling answer.
More questions? Maybe some. This is our final talk, so maybe some words by the organizers. Nahum?
So I will stop sharing in that case, okay?
Sure. Thank you very much. Yes.
Thank you very much.
Just want to thank everyone for participating. It's a wonderful tribute to the memory of Boris Drachenbrodt, and the wonderful talks, the wonderful memories. Thank you all. And hope to see you all after the pandemic. There will be, yes. So as you know, the hope is that Flock will take place next summer at the Technion in some physical fashion. And LIX and many other conferences will be part of it. And there will be a special evening session also in honor of Trachtenbrot. And the Trachtenbrot family are funding several prizes for graduate students, and details to be announced. And hope to see you there. Thank you.
Thank you.
Thank you for organizing it. It was a wonderful meeting.
Thank you.
Thank you. Thank you all.
Thank you all.
Thank you. Thanks, Nahum, Arnon, and Alex, for your great effort. Thanks a lot. And thanks to everybody.